Or questions from last time? All right. Well, the last thing we covered last time was relative motion. And the relative motion equation said if you're trying to track the motion of a particle P, the position of P relative to a coordinate system A is equal to the position of the particle relative to a coordinate system B plus the position of the coordinate system B relative to A. And then all the subscripts stay the same for velocity and acceleration. So the velocity of P relative to A is equal to the velocity of P relative to B plus the velocity of B relative to A. And the acceleration of P relative to A is equal to the acceleration of P relative to B plus the acceleration of B relative to A. Where A and B are two different rulers that have the same positive direction. Okay, so those were A and B. So A and B are each choices of a zero position that are not the same, and they can be moving at different velocities, different accelerations from each other. These rulers are moving relative to each other, and this is a way to use the measurement in one to calculate the motion of particles in the other one. So let me do two more examples. Okay, so there's a river. There's the shore. I don't know if I can draw this. There's a tree. So far, it's not so hard to draw. And hiding behind the tree is, lurking behind the tree is the school swim coach. He's supposed to be like looking around the side secretly. And in the water is this student at his school. He's trying to decide whether he wants to recruit this swimmer. So a swimmer jumps into a moving river. As the school swim coach lurks behind a tree. Write it. Coach, okay, so he has a stopwatch, okay? And the coach measures the swimmer's speed at 1 meter per second. And he's moving east relative to the ground. After the swimmer leaves, he measures the speed of the water. At 2 meters per second, moving west. And the question is, how fast would the swimmer be in a pool? So the way we want to do this is we know that the velocity of the swimmer relative to the ground is equal to the velocity of the swimmer relative to the water plus the velocity of the water relative to the ground. Okay, so look at those subscripts real quick and just verify that that fraction multiplication works out the way you expect it to. Okay, so the waters cancel and you're left with swimmer over ground. We have to choose one of these two directions to be positive and one to be negative. So let's say if that's north, south, east, and west, everything's happening east and west. So one of these two directions is going to be positive and one's going to be negative. Let's choose west to be the positive direction. This will work either way. And now let's think about the numbers that we're given. What do they give us? So the coach measures the swimmer moving 1 meter per second east. What velocity does that give us? It's -1, right? And which one of those three velocities in that equation does it give us?
Swimmer to ground.
Swimmer to ground, yep. So we have -1 meter per second is equal to, do we know the velocity of the swimmer relative to the water?
No.
No, do we know the water relative to the ground? Yeah, so this ends up being -1 is equal to velocity of the swimmer relative to the water. Plus, what's the velocity of the water relative to the ground? +2. And so now we'll solve for the speed that the swimmer moves relative to the water, and you get v swimmer relative to the water is equal to 3 meters per second. Any questions about that one? So does the coach recruit him or not? That's the important thing. I don't know either. I think that's probably really fast. Maybe, yeah, right, I think it is. Still, the coach is too lazy to recruit him. Okay, that makes sense. Let's go on to one more. Yes? No, we did the algebra to, thank you. Yeah, do the algebra. So that means, I'm glad you said that. So the velocity of the swimmer relative to the water is 3 meters per second east. We assume that the swimmer can swim equally fast in any direction, so that doesn't end up really being part of the answer to our question. But yes, you're exactly right that the velocity of the swimmer relative to the water is -3. One more. Let's say an airplane moves through the air with an acceleration of 9.81 meters per second squared down. Okay, so let's first wrap our heads around what that means. Ordinarily, if you're in an airplane accelerating down at 9.81 meters per second, you're in a very bad situation. But astronauts train on this thing, they call it the vomit comet because it makes you feel very sick apparently, but where this airplane goes through a long parabola and it's powered by its motor, but it goes through this motion that simulates a projectile motion. And the whole time it's going through that arc, its acceleration is 9.81 meters per second squared down. So we're going to see, why would it do that? And so if an object on the plane is dropped, what's the object's acceleration as observed by a passenger? Does anyone just happen to know what the answer to this is? It's going to be 0, right? And that's why astronauts train on this thing, is because it simulates weightlessness. Nothing has the acceleration like it falls. So things just hover in the air. People just hover in the air. But let's see how the math works. So the acceleration of the object relative to the ground is equal to the acceleration of the object relative to the plane plus the acceleration of the plane relative to the ground. Choose our positive direction up. So what do we know? Do we know the acceleration of the object relative to the ground?
No.
We do, because it's in free fall. And anything in free fall has the same acceleration relative to the ground if air resistance isn't an issue. And in this case, it wouldn't be, because the plane is preventing this thing from seeing the air. You know, it's the only air it sees is air moving with the plane on the inside of the plane. So this is negative 9.81 meters per second squared. Do we know the acceleration of the object relative to the plane? No, that's what we're trying to find. And do we know the acceleration of the plane relative to the ground? Yeah, that's given. That's negative 9.81 meters per second squared. And so solve for the acceleration of the object relative to the plane, and you get 0, which is apparent weightlessness. Another thing that's worth noticing, I think, about this kind of setup is a lot of people have heard, in school or whatever conversations that the reason astronauts have to deal with weightlessness is because you're so far out in space that there's no effect of gravity on you. But that's actually not how it works. When you're out in space, they're still in orbit, which means they're still feeling the pull of Earth's gravity. That's the thing that creates orbit. If you're even if you're standing on the moon, I mean, the moon is in orbit around the Earth, so obviously you're still under the influence of the Earth's gravity. The reason that in space also there's apparent weightlessness is because you and your spacecraft and the moon or whatever are all in this free fall motion that comes from the effect of gravity. But since you have that acceleration due to gravity, everything appears to have an acceleration of 0. So it's this same effect that actually makes astronauts appear weightless in space. Any questions about that? All right, so now we're going on to the next thing. We've been talking about kinematics of a particle along a line. And actually, some of these can be, some of the things we said along a line can be generalized to one-dimensional motion in general. That's not along a line, like a bead moving along a wire is also a one-dimensional motion. Now we're moving from kinematics in one dimension to kinematics in 2 dimensions. In 1D, at any instant, a particle only has 2 choices of what direction to move. You can think of it as forward and back. Label one of those directions positive and one negative. Since there are 2 signs, plus and negative, we can represent direction perfectly well with just using the sign. In 2D, we can't do that. Sign isn't enough to specify direction. Because at any instant, a particle can move in how many directions? Yeah, exactly. Infinitely many direction. So we've gone from a particle that has a choice one way and a choice the other way to a particle that can go in any of these directions. And so for the quantities that we deal with that have direction, and those are, so the kinematic quantities that have direction, that is position, velocity, and acceleration. Need a new mathematical object to be represented. A new mathematical representation. Anybody have any idea what this new mathematical representation is going to be? Vectors, yep, exactly. How many of you have seen vectors briefly before? Everybody at some point? Okay. Have you dealt with it a lot, like in math classes, or just sort of in passing? Yeah. In math? Okay. Like in trigonometry?
Yeah.
Okay. Okay.
Like at the end.
Yeah. Okay, good. So a vector is a mathematical object with two properties. Direction and magnitude, yep. Direction and magnitude. And you can think of a vector as represented in space by an arrow. Think of a vector as an arrow in space. Where the arrow's length is its magnitude. And its direction is where it's pointing. So there's a vector. That's the way to think of it physically. And this is its magnitude. A vector itself doesn't have any units, but it can represent quantities that have units. So if you're talking about a position vector, you can think of this vector as having units of meters. If you're thinking of acceleration vector, it can have units of meters per second squared. And you can do vector math as follows. This is what you call a graphical approach to vector math. First, you can add two vectors. So say we want to add this vector plus this vector. That's not how you spell the number 2. So the steps to add these is first put the tail of one vector at the head of the other vector. Head is the like arrowhead, tail is the other end. So put the tail of one vector at the head of the other. And then second, the resultant vector, that's the sum, is the arrow, the vector going from the free tail, the tail that isn't touching a head, to the free head. Okay, so just take these with your little mechanical electronic pencil. Oh, it won't let me, son of a. Okay, so I'm going to take this one there. I need more room. Okay, and then I'm going to put the tail of the other one at the head of the first one. Then the resultant vector goes from the tail that's not connected to anything to the head that's not connected to anything. Sheesh. This one's going to work. And not really. Okay, so this is the resultant. How do you know which vector to put? The tail of which vector goes at the head of which vector? It doesn't matter. The order doesn't matter at all. So I could have also done this. Put the tail of the other one at the head of the first one. And you get the same resultant vector. Okay, so they start in different places, but the direction and the magnitude are the same, and that's all. A vector doesn't have like a location. A vector only has a direction and a magnitude. Okay? So notice order doesn't matter. So vector A, and when I talk about vectors, I'm going to give it this vector symbol and arrow over the top. So vector A plus vector B is the same thing as B plus A. So what kind of operator is that? Vector addition has the property of being yeah. So in other words, vector addition is commutative. Okay, so if you have this vector and you're adding it to this vector, what do you get? Take a minute and just do that on your notes. All right, so to add these, put the tail of one at the head of the other one, it doesn't matter which. And then the resultant vector goes from the free tail to the free head. So you could describe this a few different ways. You know, if you didn't have any numbers put to this, but those were drawn carefully, you could take a ruler, measure it, that gives you the magnitude. Protractor tells you the angle, and that would give you all the information you needed for that vector. The other thing we can do besides adding two vectors is multiply a vector by a scalar. Let's see. Okay. Multiply a vector by a scalar. What's a scalar? Scalar is just a number. So, and it can be positive or negative. So this is just multiplying a vector by any number, not multiplying it by another vector. There are ways to multiply a vector by another vector, but that's not going to be important to us yet. So I'm going to break this up into two pieces. Multiplying a vector by a positive number multiplies the magnitude of the vector by that number. But keeps the direction the same. So if you multiply 2 times a vector like this, the answer is just 2 of those pointing in the same direction. And second, multiplying a vector by -1 just switches the head and the tail. It keeps the magnitude the same. Switches the head and the tail. No change to the magnitude. So, for example, -1 times this vector is just this vector. Well, with those two things, you can multiply by any number because you can think of doing those in order, you know, multiply by the positive number and then multiply by the -1 to just switch the direction. So for example, let's say you have -2 times this vector. So there's 2 times the vector. Then we have to multiply it by -1, and so you get a final answer that's that. Any questions about that? Okay, let me give you an example to do. So just on the board, do this graphically. Let's say the vector u is this, and the vector v is this. What's 3u minus 2v? Okay, do that on the board.
You just said, why do you think we all go? Sorry.
Time to shut up now. So 3u is like this. And -2v is like this. And then add those together. 3u minus 2v is equal to put them head to tail like that, and the resultant is this. So yeah, you have to remember to put them head to tail. If you put them tail to tail, head to head, if you know anything but tail to tail gives you totally the wrong direction. It's not backwards, it's just wrong. Okay. Any questions about that? For calculations, we are not going to use this graphical approach. Well, you can use it. We usually won't use the graphical approach. Instead, we'll express vectors as components. That is a piece parallel to the x-axis plus a piece parallel to the y-axis. that add up to the original vector. So for example, if you have a coordinate system like this, the standard coordinate system, and you want to represent this vector, put the tail of the vector at the origin, and then figure out what vector parallel to x plus what vector parallel to y gives you the original vector. So in this case, it's that plus that. This is the x component. And this is the y component. These are always perpendicular because x and y are always perpendicular. One thing to notice about this is if the component is in the direction of the negative axis, then we say it's a negative component. We give it a negative number. So the component is negative. If it's in the negative axis direction. So this example here, does that have one positive, one negative, two positive, or two negative components?
Two negative.
Two negative components, yep. So if the components are Vx and Vy, there are two ways we can write this. The first one is that the vector V is equal to Vx times I hat plus Vy times j hat. I don't know where the I and the j come from, but that's just what people denote the unit vectors in the direction of, you can think of those as the way that you represent the axis directions. So that's saying it's this number times a unit vector in the direction of the x-axis, and this much, this number times a unit vector in the y direction. The other way you can write it is as a column vector or a column matrix, where Vx is here, Vy is there. Some people use, there are different notations out there, but these are the two that we're going to use in this class. But you need to be comfortable with both of these two. You'll see questions given in both of these two forms. Yep. Yeah, that means, so if you, so like in this example, if this x component here gives you the value Vx, so in this case it would be a negative number, say this is negative 5.4, then you would, and this y component, we know it's negative from looking at it, let's say that that's negative 2.1, okay, then you would write this as negative 5.4 times I plus negative 2.1 times j. It's just a notation, but that the I says in the direction of the x-axis, and the J says in the direction of the y-axis. And what that hat means really is, you know, the funny hat on the I and J, that means it's a vector, but it's a vector that has a magnitude of 1. So you can think of it as just a pure direction. Okay. So when you multiply, what happens when you multiply a number, the number negative 5.4 times a vector with a magnitude of 1, what you get out is a vector that has a magnitude of 5.4, or a number 5.4, in the direction of this. So it's sort of a way to split it up into a pure number and a pure direction. And then this is just a different way of writing it. It means the exact same thing. So now we have to figure out how to find those components. First, find, okay, no, erase that. Put the tail of the vector at the origin of the coordinate system. Second, find the counterclockwise angle from the positive x-axis to the vector. And the vector components are the length of the vector times the cosine of theta, length of the vector times sine of theta, or equivalently, you can write that as L cosine theta I plus L sine theta J. So it's, what you're doing is just trigonometry. And I should say here, you can also just use right angle trigonometry and get the signs, the plus minus signs, from what quadrant you're in. Okay, so let me do an example. So let's say we're in this usual coordinate system. And our vector has a length of 10 and makes an angle of 30 degrees with the horizontal, like this. So let's say this is the vector u. We want to know what are the components of u. Well, we'll put the tail at the origin. we know that this angle is 30 degrees. And so counterclockwise, what angle do you have to follow to get to the vector? 330, or you can also just say negative 30 and go clockwise. Clockwise angle is negative. And so vector u is 10 times the cosine of negative 30, 10 times the sine of negative 30. And so that is 8.66 negative 5. Let's do it thinking about it as right angle trigonometry. So the other way you can do this, and you should get comfortable with both of these two ways because both are useful at different times. So there's the coordinate system. There's the vector. The components are this and this. This angle is 30 degrees. This is 10. And so now you can just do right angle trigonometry to figure out those lengths. So this has to be 8.66. This length has to be 5. And now from the quadrant, since this vector is pointing in the fourth quadrant, we know it has to have a positive x component and a negative y component. And these two are because it's in the fourth quadrant. Notice that finding the components of a vector is exactly equivalent to putting the tail at the origin and finding the coordinates of the head. Any questions yet? Coming up with components is dependent on the coordinate system you choose, just like finding the coordinates of a point depends on the orientation of the coordinate system. So now let's think of the same problem we did last time. So we have a vector that has a magnitude of 10 and makes a 30-degree angle with the horizontal. But this time let's figure out the components in a coordinate system like this, where that's a 20-degree angle from the horizontal. So there's the coordinate system. There's the horizontal. there's the vector. This angle is 30. This angle is 20. And so you can calculate the components of this vector as 10 times the cosine of negative 50, 10 times the sine of negative 50, so that is 6.43, negative 7.66, I think. And you can also write that as 6.43 times I minus 7.66 times j. Okay, so what's the benefit of writing vectors in components instead of just measuring them? It makes all the math really easy. So putting vectors in components makes vector math easy. So first of all, adding two vectors. If you have the vector AB and you're adding it to a vector CD, the vector you get out is just, it has an x component of A plus C and a y component of B plus D. Or if you're using the other notation that says, if you have A I plus B J, and you're adding that to a vector C I plus B J, what you get out is you add up all the things multiplied by the I, so A plus C times I plus B, the quantity B plus B times J. And then, yes?
Oh, I was just wondering for when we, in the example, when we rotated, like, why did we do that?
I didn't give a reason, but some problems are easier in certain coordinate systems. And let me show why, what makes it. Like fundamentally, problems, you can just do them in any coordinate system, it's all the same. But in some problems, if you line up coordinate systems with the coordinate axes with most of the vectors you're going to see, which you sometimes can do, you can just eliminate having to do trigonometry as much, so it saves you some time. Think about this. So say you have a vector that has a length of 20, makes an angle of 25 with a horizontal. What's the easiest coordinate to represent that vector in? Well, it would be a coordinate system like that. Because in that coordinate system, the entire vector is in the x direction. And so you could just represent this vector as 20, 0, or 20 times I. Okay, so it's just to simplify the math a little. Sometimes we'll do that. For now, we're not going to do it, but in a couple weeks, we'll start seeing some advantages to that. Any other questions yet? What's the other kind of mathematical operation we want to do on vectors? So that's adding vectors.
Dividing?
Well, multiplying by a scalar. So we're doing the same two that we did before, you know. So second, multiplying a vector by a scalar. And so if you want to multiply the scalar c times the vector a, b, you just multiply both components by c. So you get ca, cb. And that works whether c is positive or negative. And with the other notation, we have c times the quantity ai plus bj. And that comes out to be ca times I plus CB times J. So now to put these two together, if you have 2 times the vector 5, 1 minus the vector 0, 4, I'll multiply this one out so we get, so 2 times this vector is 10, 2. And we're subtracting 0, 4. So 10 minus 0 is 10. 2 minus 4 is negative 2. And that's a lot easier than trying to carefully draw out the directions and the angles and everything. It's sort of interesting that that simple way of doing the component math works out exactly to be exactly equivalent to that graphical method. You can actually, if you sort of think about it in terms of breaking up every vector into components, you can make sense out of why those are the same thing, but I think for most people it's not totally immediately apparent, but they are equivalent. All right. Here's one for you to do. So let's say the vector u has a length of 5 and makes an angle of 45 degrees with the horizontal. And the vector v makes an angle of 20 degrees with the vertical and has a length of 2. So what's 2u minus v in components? Oh, and I didn't give a coordinate system. I guess anytime I forget to give a coordinate system, it's because I'm assuming we're using the normal one. Okay. Okay, so the components for u are 5 times cosine of 45, 5 times sine of 45, which is, well, I'll just leave it like that for now. And the components for V are 2 times the cosine and sine of 250, or negative 110. And so 2u minus v is equal to 2 times this, which is 10 times the cosine of 45, 10 times the sine of 45, minus 2 times the cosine of negative 110, 2 times the sine of negative 110, and let's see. This is about 7.071, 7.071. This one is 1 point, like negative 1 down here, negative 1.880. And this one is negative 0.684. And then I can't do those in my head. What do you get when you subtract that? 7.755, 8.95. Okay. Any questions about that? There's one other type of calculation that'll be useful sometimes. And that is, given vector components, calculating the magnitude of the vector. Well, that's just the Pythagorean theorem, because if you have a vector like this, and the components are like that, let's say this is Vx, this is Vy, this is the magnitude, then the magnitude is equal to Vx squared plus Vy squared square root. Yeah, and I should point out, maybe it occurs to you naturally, but what happens with vectors, so with numbers, everything is either in the same direction or the opposite direction, right? Things are either positive or negative. And so when you add numbers, all you're doing is adding or subtracting from the magnitude. That's not true with vectors. So like when we added these things, the magnitude of the final answer is not the same as 2 times 5, minus 2. It doesn't work like that because they're not in the same and opposite directions. They go off these funny directions from each other. And then sometimes we'll have to do calculus with vector components. The key is that you can just treat the components separately and do calculus on the individual components. So just treat the individual components separately the way you would with numbers. Way you would with numbers. Okay, so for example, what's the time derivative of let's say that v is equal to 5 2t. So what's the derivative of v with respect to time? And what's the integral of v with respect to time? For a to take the derivative, you just take the time derivatives of the individual components. So v dot is just equal to 0, 2. And for the integral, same thing, take the integral of the individual components. So you get that the integral is equal to 5t plus c1, t squared plus c2. Bless you. Any questions about that? So now that's all I'm going to say about vectors. I think the assignment that I'm going to give you today is going to be just nothing but vector calculations, plus old stuff. And so now that we've defined vectors and talked about how to do math with them and stuff, now we're ready to talk about what the position vector means, what the velocity vector means. We're ready to talk about physical quantities in terms of vectors. No. Okay, so now kinematic quantities as vectors. And just like I did with one-dimensional kinematics, I'm going to start with the position vector. So first of all, think about what we needed to specify in order to give a number to a position in one-dimensional motion. So to define a position vector, to find the position, let's compare what we need along a line to what we need in 2D. So what did we need to define for position along a line in order to put a numeric value to the position? two things. We needed that to have a position versus time function, but just to specify the position, there were only two, not that one. Positive direction, yep.
And then the start point, wasn't
It wasn't the start point, it was the zero position,
zero.
which sometimes is the same, but they don't mean exactly the same thing. So the zero position is just where you're setting down your measuring stick. And in 2D, you need to specify one thing, the coordinate system. But that is made up of two different things. Coordinate system, to specify that, you need to specify axis orientations. And you can probably see the relationship between choosing your axis orientations and choosing your positive direction. And then the second thing we need is an origin location. And that's just the two-dimensional version of choosing what you're going to call zero. So once you make your coordinate system choice, position vector, and we're going to call it lowercase p vector, is a vector from the origin to the object. So if this is your coordinate system, and this is the object, then that's the position vector. The units for position are, the units of everything are the same that they were in one dimension. So it has units of length, SI units are meters. And to determine the position as a function of time, or to plot position components as a function of time. So to express the position as a function of time, p of t, and you can write a vector as a function just like you can with a scalar value. You need to make a third specification. And that's the zero time, the instant corresponding to zero time. Now, there's no real obvious way to plot a position versus time graph like there was with motion along a line, because you have two separate components going on. And so the best you can do is plot those individual components. We're not going to do that real often. But notice it's much more awkward to plot position versus time now. In 2D. The best you can do is plot the x component of the position versus time and the y component of the position versus time separately. Any questions? Okay, well, let's stop there, and I guess on Tuesday we'll start with the velocity in 2 dimensions.